It's a great pleasure to introduce, in fact, it's not introduced, to reintroduce Pierre-Louis Lyons. He has been here quite frequently, and is always very interesting mathematics he presents. So he has been changing from Boltzmann to viscosity solutions, and now on mean-field games that promise to be very exciting and remarkable as he is. That's enough.
That's already too much.
Go ahead.
Well, thank you very much, Jacques. It's as I already said yesterday evening, it's a great pleasure to be back at IMPA. I've been here several times, and I guess they know me because, observe, yesterday evening, talk from 6 to 7, afterwards dinner. Today, talked from 6 to 7, and there is a cocktail afterwards. They know what they need to do in order to get me to give a talk. Huh? I don't know what reputation I have now. So my voice is a little more low, is a little bit lower than yesterday, probably thanks to all the caipirinha yesterday evening. Anyway, I first need to apologize for at least a few people sitting in the audience, because I cannot assume that everybody knows what the midfield games are, and I keep on, having to explain what they are, how they appear, and before getting to some real mathematical stuff or some new stuff, and in the end, I never get to the new stuff. Sorry for I can see at least less than 10, probably about 10 people that have already heard part of this lecture, but I have to start from scratch. It's a joint project with Jean-Michel Lasserie. In a recent talk, I even mentioned that it's an endless project with Jean-Michel. Maybe for all of you, I should explain who is Jean-Michel Lasserie. He is, in some sense, an amateur mathematician. He's probably the most original, creative guy I ever met. Just absolutely amazing. Okay, so there's going to be a long introduction, which is, as usual, real blah, blah. It's going to be really about blah, blah. And then I'm going to give you, as I did many times throughout the years, a really simple example. From time to time, I call this example S example. S can be either simple, like in this presentation, or you could also replace by stupid and silly. It works as well. And there will be more stupid examples on the way. Huh? Don't worry. Creating stupid example is something I'm particularly gifted at. Anyway, general structure, two particular cases, overview and perspectives. I always dream of doing trying to do what Orson Welles did in his last movie. His last movie was F for Fake. It was about the art business and in particular, well, anyway, that's a long story. But Orson Welles appeared at the beginning of the movie and said, everything which is going to take place in the last 15 minutes of the movie is completely false. And of course, you completely forget it. And when you get at the end of the movie, oh, really, this is true about the life of Picasso? And then Orson Welles comes back and says, remember what I told you in the beginning, right? So I always dreamed of doing something like that, something completely stupid, completely false at the end of the lecture. I cannot do that. I mean, this is too much, too much education prevents me from really doing that. But what I'm going to do instead is to switch to something which apparently has nothing to do with PDEs, mean-field games, and so on, which is machine learning and social networks, right? Okay, so that's going to be the last 15 minutes. It's not false, it's different, okay? So, Yeah, so usual blah blah, it's a new class of models for the behavior in mean field sense, like in statistical physics, statistical mechanics, for the average behavior of a large number of agents, small agents. And we saw that in the early 2000s with Jean-Michel Assery. In fact, our main motivation comes from a big operation sponsored by two private companies in France, which is called Finance and Sustainable Development. And when you start studying about all the game strategies which are being played for non-renewable or just partially renewable commodities, oil, phosphates, and so on, there are lots of questions that you would like, that economists call externalities, that you would like to try to model. And that was, in fact, the motivation. But the first example that we treated, I remember very well, was Jean-Michel bumping in my office without even knocking at the door. He never does that. Bumping in my office and say, OK, we're going to make a model for the traffic, cars, around Arc de Triomphe. So some of you may know what Arc de Triomphe is. It's this square, which is circle, in the center of, in some part of Paris, and usually there's quite a little bit of traffic. And if you look at the traffic, it's being organized in circles when it's not too fluid or not too congested, okay? And so he started writing things that made absolutely no sense with one sign mistake by line of computations. And in the end, he said, here's the equation. Laplacian u equals 0. I said, wow. But then I know this guy, and I told you, okay, wait. The equation is irrelevant. He was very, very excited. He said, okay, spherical symmetry, level sets are curves, those are the optimal trajectories. End of the proof, we have a model for the traffic. I said, okay, let's forget the traffic, and what did you write? He said, I don't know. And so we started. It was the beginning. And in fact, we were quite lucky. So it's also good for mathematicians that need, after all, to make a living out of mathematics. So it requires lots of new mathematical theories. There are lots of applications: economics, finance, social networks, crowd motions. If time allows, I will show you a few, two movies about a crowd getting out of a big hole. Which is in fact now absolutely necessary whenever one builds a big, like a big conference hall, a big music hall, or anything of that sort, where there are lots of people that have to be in such a room. At least in countries like France, you have to give, at the same time, to get the authorization to build some numerical simulation about how people are going to get out of the room. That's fact. Doesn't mean that those numerical simulations are really realistic. You just have to produce something. I certainly want to mention Malamé, Keynes, and Wang in different order that introduced a particular class of mean-field games model completely independently. And in fact, honesty forces me to say that probably the first time someone thought about the mean-field games was people in economics. Two brilliant economists named Krassel and Smith, who wrote a paper to make models of agents, economical agents in macroeconomics. They never write any kind of equations, even didn't make precise the model. What they said, as I already mentioned yesterday, at least for some of you, was that they just explained what were the behavior rules of all the agents. And then they had the idea that, well, it's better to think of density of agents and trying to track. And that was it. No model, no real model, no equations. And then they made a numerical simulation, and there are various consequences. It has remained a mystery. It has had a huge impact in macroeconomics, also because people really couldn't understand what the model was. In fact, it's the first example, which was brought to our attention by Bob Lucas, a famous economist who won the Nobel Prize in Economics a little while ago. It's a research community in expansion: mathematics, economics, finance, computer science. I show, I mean, there are people in networks, in communication networks using min-field games. I just got a paper where people in the United States use min-field games for the management of a fleet of electrical vehicles, etc., etc. People in Portugal using min-field games for the games management of a big array of sensors in the sea for fishing and so on. So there are some practical engineering applications that are beginning. Okay, so there are some written references, but I've been a little bit lazy those last years. Most of the existing mathematical material about what I'm going to say. Fortunately, other people now are moving in the fields and are really writing papers and so on. So there are now a big bibliography on min-field games. And, but if you want to see the origin and some developments, in particular about what I'm going to say today, you can download all my courses, which are each year different, at Collège de France. So it's 4 times 18 hours. You can download them if you want. Huh? I recommend them if you have trouble sleeping at night. It's a combination of min-field theory, as I said before, classical in physics and mechanics, and the notion of Nash Equilibrium in game theory. So basically what we are trying to describe is our Nash Equilibria for large number is going to become an infinity, a continuum. First, mathematical idealization, and second, big assumptions that all those players somehow are small compared to the community, to the crowd, to everything. In some cases, which has triggered a lot of attention on those models in the probabilistic community, starting with René Carmona and many, many other people now, there are various interpretations using the idea of controlling processes like nonlinear Markov processes in the sense of McKean. Also, one of the basic assumptions which is underlying everything I'm going to say, that each of the players is supposed to be rational. Rational is a very vague word. Economists use it in with a rather specific meaning. Here I'm trying to, I will use it in a very broad sense. What that means is that the behavior of each agent is going to be dictated by a certain mathematical criterion that he's trying to optimize, and the criterion, possibly the dynamics, depends on all the other players. But there is something that he would like to minimize, okay? This is clearly an assumption. So you can say people are not such rational beings, but that's certainly something which is needed in order to do some mathematical models, at least this type of mathematical models. With this general definition of rationality, herd behavior is rational, because what you want to do is the same as the others, okay? So don't think that rational in any usual sense. It's really, there is a criterion that needs to be minimized. Okay, so it's unfortunately a huge class of model which make the mathematical analysis almost impossible in general, because just to give you an idea, when if the agents lose their freedom to decide, they become particles. And so you should have, as particular case, all the min-field equations in classical physics and classical mechanics. And that's quite a bit, because that's one of the game which has been the most played in physics. Also, there is another approach to some of the issues that I'll be considering, which are the so-called, this is just a description of what's going on, agent-based model. And agent-based model are limit models of min-field games. I'll come back to that when I mention the intertemporal preference rate. Okay, so here comes a real simple example. As I said before, quite a few of you have been exposed to that example. So the two other examples I'll mention later on is the following one: at which time a meeting should start. Okay? So suppose that we have a meeting, a talk, like this one. Quite a few number of people have to participate. You are in a civilized country, so it's not going to start on time. Okay? And it's going to start when there are enough people being measured, like, let's say, 85% of people are there, right? Rough estimate. Okay? So this is a game. I'll explain later on why I care about this silly, stupid example. The other example I certainly want to mention is an example I like very much, is the example of the ola. Ola, the Mexican wave in Northern America. You know, it's something that people do in a stadium, okay? People go and see a football game, a rugby game, and then from time to time you see this wave propagating in a stadium. People are not being even paid to do that, and still it goes on and on and on. There is a big literature on the ola. I'll come back to that later on. So I just want to keep you awake by saying that there are things which can be which might be understandable at some point. Okay, so metric space, forget it. It's going to be a part of RD. And here's the game. It's just choosing a location in that space. So you have n players. They just want to choose one location. So a typical example is you go to the beach in a country where you don't have thousands of kilometers of beaches, so they are rather crowded, so it could be Rio. That's reasonable. You go to the beach. In fact, it's in some sense the dual problem of a problem raised by Otteling, a famous Dutch economist, who asked the following questions. There are people on the beach. Where should ice cream vendors put their cart? Okay? It's a very classical problem and far from being easy. So here I'm assuming that it's a dual problem. I'm assuming that the ice cream vendors are there, the places where you can eat and drink are there, and you want to put your towel on the beach. The model is not going to teach you where to put your towel. You know how to do that. You don't need me to do that. The question that I want to answer is, if everybody behaves in a similar fashion, because the criteria are about the same, not being too far from one of the interesting spots, and not being in a place which is too crowded. I mean, that's what most normal people would choose as a criterion. So if they all share the same criterion, what kind of distribution of towels should we expect? Okay, so that's a question. Okay, so but these, before I give you the answer, or you know, the type of answers provided by such models, let me describe the notion of a Nash equilibrium. So a Nash equilibrium in general is given n functions of n variables. So you have n functions of n variables, and each the player I, choosing the position xi, would like to minimize the fi function. Of course, it depends on all the others. So you cannot simultaneously minimize n function, and Nash, in essentially 2 pages paper for which he got the Nobel Prize in economics, invented that notion of Nash equilibria. So what you do, it's really a fixed point idea. So you freeze all the O players. Suppose you are the ice player. You freeze all the others. So then you're left with a criterion that depends only on your location. And the point which is supposed to be part of this Nash equilibrium, the xi bar, should minimize that function of that remaining variable. So given all the others, you minimize the criterion. But of course, once you have minimized your criterion, it should be consistent with the minimizations of the others, because then you get frozen when the others choose. Okay? So that's a notion of a Nash equilibrium. And in order to make already a little preview of things which are related to machine learning, here is an exercise in algebra for you. Okay, so take an n by n matrix, n by n matrix, symmetric matrix, and what are the, take k smaller than n, what are the Nash equilibria of the following problem? So I'm going to write the fi function also. It's going to be fi of cap x, meaning all those x1, xk. And so it's going to be the quadratic form associated to A. And then here, let's put a large constant that depends on the matrix A, large enough. And here what you put is a sum from I different from j of the absolute value of the scalar product of xi and xj. Okay? Why not? The answer is, what are the Nash equilibria of that? Well, exact penalization, that's an L1 penalization, exact penalization for C not large enough, means that you should expect to get a set of vectors which are orthogonal to each other. And then they compete to minimize AXI, XI. So then you can guess the answer. So for simplicity, to avoid all kinds of multiplicity, let's assume that the eigenvalues are simple. Take the k first eigenvalues, take the subspace generated by the k first eigenvalues, then the Nash equilibria are any orthonormal basis of that subspace. Not only eigenvectors, it's really the projector that you get in that manner. So it illustrates one point. I'll let you work on that example. But it illustrates the fact, which is the difficulties with the notion. It is certainly an interesting observation about spectral projectors. It's in fact useful because later on I'm going to explain why many questions which are related to machine learning are naturally mean-field games, are naturally set in the context of Nash equilibria, and probably in lots of practical applications of big data. One of the things which is done most in order to do the clustering of data is to use the SVD, singular value decomposition. And this, in the end, is about computing the first k eigenvalues. But already there, when you want to compute the smallest eigenvalues, it's natural to think of it as, in fact, directions that compete with each other. So there is no player. It's just a vector, right? But you can have an interpretation in terms of games. I'll come back to that later on, not that example, but those ideas behind data analysis. So usual difficulty with the notion, incredible non-uniqueness. You may have also Nash equilibria which are not very relevant and so on. Existence is not that simple neither, and so on. Question is, as n goes to infinity, might it be possible that it becomes simpler? Okay, so clearly, if we take n-body problems in classical mechanics or in quantum mechanics, it's even worse. With n even not very large, it becomes extremely difficult. On the other hand, if you let n go to infinity, you add lots of equations, so then you write Navier-Stokes lots of type equations, or you add Boltzmann equations. You have things that you can use to compute and give the good description of what's going on, because you have lots of gas molecules. And there is thermodynamics, there is equilibrium, and so on and so on. But that's another story. Okay, so could it be that in game theory, there is something of that sort? Well, the answer, fortunately, is yes. Otherwise, we would be out of job. Anyway, so n going to infinity, is it going to be any simpler? We're going to do, of course, the same type of assumptions which are being made in statistical mechanics and statistical physics. Here, what I'm going to say later on, I will mention variance. We are going to have a single population, a single homogeneous population of agents. Then you can move having 2, 3, a few, or no, 10, 20 different populations which are still homogeneous but are different from each other. Okay? So only one populations, and they are indistinguishable. I don't want to say, you can think that those are human beings, I don't want to say they are identical. So indistinguishable, what does that mean? This means that if we all go to the beach, the fact that I'm called Pierre-Louis or I'm called Jaco won't make a difference, right? On the density of towels. exchanging labels is not going to make any difference. So indistinguishable players means that seen from the I guy, the xi guy, I myself, all the others are the same. So I can make permutations of all the others. They should have the same contribution to the criterion. So which means that this function that a priori depends on n variables should depends on n minus 1 variable in a symmetric fashion, and of course depends on my choice. My choice is xi, so it depends on xi and a bunch in a symmetric fashion of n minus 1 variables. Then, of course, I can be exchanged with another player, and what that means is that this function f should be independent of I. It may depend on n, but that's another matter, okay? So that's what indistinguishability creates in terms of a criterion. So this, you may say, well, this is very, very particular in terms of listing n functional. Yes and no. It's certainly mathematically very, very specific. On the other hand, everything which is related to non-uniqueness and difficulties with Nash player is still there. In fact, that's a good example. This example has exactly those features. Okay, so and there is a form, and there is quite a large non-uniqueness because you have a continuum of Nash points. You can do all rotations. Certainly, this assumption is not going to simplify the level of n, is certainly not simplify a lot. So part of the mathematical series, and then I'm just scratching the theories, is to have some kind of mathematical framework which is independent of n. So when you say, forget the xi, that you have a function of n minus 1 variables, and that this function is symmetrical in n minus 1 variables, and so what? When n moves, this moves, and you would like to have a single setting. The answer is that what you should really look are functions which are defined on the state space, E, and on the set of probability measures on E. And the way you think about it is that points are being replaced by the empirical measure, 1 over n minus 1 sum of all the Dirac masses at those points. It's certainly automatically symmetric, and in fact, there is a general statement with the appropriate moduli of continuity, which tells you that as n goes to infinity, it's always of that form. And then you can prove a theorem that Nash Equilibria converge as n go to infinity to solutions of, here is a min-field game, okay? I'm not saying this is new. This is so simple that people had thought about things of that sort. Nash Equilibria converge to solutions of that problem. So what is this problem? This problem is that I'm going to fix all the others. That's a Nash Equilibrium spirit. All the others, that's M. And I'm going to look, in fact, at the density of towels, the probability distribution of towels. I'm going to look, that's going to be the unknown. I will be searching for an M, which is a probability measure on E. I freeze M, this means freezing all the others. You might say, well, you're also freezing yourself. No, because I contribute very little. Well, I'm neglectable. The self-counting of one person is irrelevant. So that means that I freeze M, I look at the set of minima, and I want the support of M to be included in a set of minima of that. Why is that so? Well, because I'm going to take any agent, any player, and clearly, what is the definition of player? It's a guy who sits in the support of the distribution of the probability distribution of players. Of the support, there is no one. There are no players. Okay? So for any x in the support of M, it has to be a minimum of the function where you freeze M. Again, this idea of fixed point, again, Nash Equilibria. And again, a problem which is not that easy to, it's a fixed point problem. Right? I get M, look at the set of minima, check the support. If not, you would like to iterate how, that's another matter. Okay? So in fact, it turns out there are general existence and stability results. There is uniqueness when you have a monotonicity assumption on which I will come back. And in a very particular case, you have an optimization interpretation, which I don't want to insist upon. So here's the example of the beach. So either a line or a strip. And so what I'm going to say is that I'm going to look at a function f of x and m. It's just an example where I have first a function which measures a position. So suppose that we have 1 point, okay? 1 point of interest. So a typical function for the position is going to be like x squared, right? Being exactly at the point may not be a very good idea. It's very hot. I don't want to walk a lot. So x squared is just to give an example. Then I want to have something which measure, and that's going to be position against the others. And so I'm going to count how many people are in the neighborhood. Okay? So what that means? This means that I'm going to count the numbers of those j's for which xj minus x is less than epsilon. Okay, so that's really I should, that's the empirical measure of the n minus 1 players, and that's xi. Okay? So I'm counting all the other players, among all the other players, those which are in a certain neighborhood, so there is a certain scale. And indeed, you can say it's 1 or 2 meters, 10 meters that's the order of magnitude. That's a typical scale. If you were interested in the populations of cities, you would have a different scale. If I have time, I'll talk about population of cities. Very interesting question. So you normalize it, you look at the frequency, and I like to normalize by everything, so I also normalize by this scale. So epsilon may not be small. I'm just writing epsilon because in a minute I let it go to 0 in order to have something which is simpler to understand. And h measures how much you want to be or you don't want to be in a crowded place. So when h is increasing, what you have is aversion to a crowd. Okay? Because you pay a lot if there are lots of people. So that's normal people. I cannot resist. I always say the same joke at that point. And then h decreasing means that really that's herd behavior. Huh? So normal people tend to avoid large crowds when they go to the beach. But there is one population of abnormal people that just want the contrary, and they are called teenagers. And suddenly, oh, look, it's desertic. We'll look at the two cases. So anyway, so this is the description at the finite level. Let's move on, and here it's up there above, except that it's a G instead of an H, but that's okay. So the general formulation in terms of measure is that gadget, f of x, plus G, and then what you have clearly is a convolution product with the indicator function, the normalized indicator function of the ball. Let me take epsilon go to 0 to play a little bit the Boltzmann-like game. So it's n going to infinity, radius going to 0. Here I'm doing it very naively. And what you get is this functional f of x plus g of f of m of x. And that's the MF Minfield games. You want to look at all the minima of f of x plus g of m of x. M is the unknown. And you want all of the points in the support of m to be in the set of minima of that function. Not clear how to solve that. It turns out that indeed there is uniqueness when g is increasing and non-uniqueness if g is decreasing. And that's natural. And in addition, you have a minimization problem in that example. I let epsilon go to 0 precisely to have an explicit solution in that example. And in fact, through that minimization, you obtain the explicit solution. Okay, before I comment the explicit solution, let me go back to uniqueness, non-uniqueness. Crowd aversion, avoiding the other people, this will tend to create a natural and nice density. Now, if, on the contrary, you want to be in locations which are very crowded, then it's clear, if there is a point, people are going to flock around that point. Okay, there might be uniqueness. Now, if you have 2 points, they can flock around any of the 2 points, and clearly you have non-uniqueness. Okay? So, this to explain a little bit intuitively while monotonicity in all these problems plays a role. I mentioned yesterday evening monotonicity in the context of strange infinite-dimensional hyperbolic equations. It's the same phenomenon taking place here. When G is decreasing, herd behavior like non-uniqueness, and in fact, you may have non-uniqueness. Okay, so the explicit solution, I promised that. So if f is x squared and g is log, which means that you're moderately averse to crowds, what you get is a Gaussian distribution of towers. Fine. I mean, I'm not really interested in the distribution of towers. It's just to give you an example on how to work with this. Okay. More examples later. And here comes the visit to the dentist. Okay? What do I mean by that? Well, you know that going to the dentist is usually not fun, unless you have very special tastes. So it's not fun, but it's useful. Okay? So here is just one example of the models. It's going to be an infinite dimensional equation. I will make connections for those of you who were already yesterday evening with me, and with the connections with the Hilbert space and blah, blah, blah. This is a very particular case, dynamical problem, finite horizon, continuous time and space, just bounded noise, both independent noise and common noise. That's a point I want to raise, is that in physics very often when you're dealing with statistical physics and you use probabilistic models, usually the noise which are affecting the particles are independent one from the other. Because more or less, having a common noise would be like shaking the whole box where you have your particles. That's a problem of interest, but of moderate interest for physics, right? And that would be a common noise. While us, certainly we have our own neurosis and so on, so clearly we have our own noise, independent from one from the others. But we are also being submitted to the general ambient noise in the economy. That's completely clear. Okay, so we might be slightly more risk adverse than the others. That's noise, independent noises. But what happens globally, the global fluctuation of the economy, and no one has any clue, can make any prediction, that's more a common noise for everybody. So common noise are really natural in economics, and common noise creates infinite-dimensional problems. Hence macroeconomics, Kessler-Smith, an infinite-dimensional problem. So the equation involves a function that depends, that is a function on x. X lies in RD, and that's part of the modeling, is how you're going to describe an agent. What are the variables that allow to describe what you want to describe in an agent? It can be age, it can be wealth, it could be location, whatever. So here, that's part of the model. You collect how you describe your agents. M, that's a probability distribution of agents. And U of x, M and T is for time, X is for the set of attributes, and M is represents indeed the density of all agents. So the type of equation you have, let me forget. I keep on forgetting I have a pointer. Before I destroyed it, not yet, soon. Anyway, so this is what I call the master equation. It's an equation that involves typically a Bellman part, that's dynamic programming, but it's also an equation that involves the derivatives operations, derivative operators in the space of probability measures and in directions which involve derivatives with respect to x. That's a mess. Okay? Doesn't mean that there is no structure, but this is a little bit messy. However, here are some little general ideas. X1, Xn, in fact, the quotient space up to permutation. You should think of these as being probabilities through the empirical measures, but you can also think of these as being random variables. L2 not omega fp. Why? because you think that you're taking those very particular random variables that takes values with probability 1 over n. Okay? So whenever you have this problem in Rn minus 1 with symmetry, you can lift it to the space of measures, and that's the type of ugly equation you get. But you should also have an interpretation where x is a random variable. As n goes to infinity, basically you get all kinds of random variables. And of course, the only thing that matters is the law of x, right? Because that's the empirical measure. Okay, so that's the connection with my talk yesterday, that if you work in that space, all this system simply becomes du over dt. Well, let me use another notation. So let me use a script u, du over dt, plus some f of x and u, x being the random variable, times grad times u equal g of x and u. And plus epsilon, it's not epsilon, that's where is it here? It's going to be alpha. And here it's going to be the Laplacian in Rd of u. By this, I mean the Laplacian associated to the translations by constant. So x plus lambda, where lambda lies in Rd. Okay? So it's quite spectacular. You have some nice f and g. There is a price to be paid for that because the u and the capital U, in fact, the answer, let me give you the answer, the u of capital X is the gradient with respect to x of this u up there at x and low of x. Okay? So if you look at this equation, it's almost hopeless to prove that it's already locally in time well posed. If you look at that system of equation recast in a Hilbert space, it's a trivial matter. Okay, well, trivial. At that stage, I realized, talking with one of you yesterday evening at dinner, that I was not clear about what that means with a gradient, with an Hilbert space, and so on. So again, let me remind you Krylov's trick, and you take the scalar product of u and a point y, and you have a new function uy, and this function du over duy over dt plus f of x uy. Okay, so look here, this is now a function that goes in from L2 into L2, right? Now this uy is now a function that goes from L2 into R. So if you think that L2, the adjoint of L2 is L2, you identify the dual with the space, then the Fréchet differential is a gradient. It's a point in that Hilbert space, and you're just taking the scalar product with gradient uy equal. So it's exactly as if you were in Fourier D. So this, it took a little bit of time to see the connection between the equation of the space of measures, equation in L2, and which the MFG are completely embedded in those equations. And which are the equations which are MFG is an even more technical matter that I don't even want to discuss. Fine. Infinite dimensional problem already said. There is one case where we split variables for the criteria and everything being gradients, where you can rewrite those Milfield Games equation in terms of optimal control of stochastic partial differential equations. Many extensions and variants, that's pretty clear. There are two particular cases when there is no common noise, independent noise, then by, in fact, doing the characteristics, so there is no Laplacian. So you know that you have characteristics. You can use characteristics to solve those hyperbolic equations. And what you should get is indeed a backward-forward equations. It involves a Laplacian, because even Laplacian for those models are hidden in first-order operations in the Hilbert space. So that's something that one needs a little bit of time to understand it, but that's no big deal. So it's not as singular as it seems. So what you get are indeed backward-forward here in that very simple example, Fokker-Planck-like equations. The first one is really a Bellman equation. And the second one is the evolution, the dynamics of the population of agents. And that's because there is no independent noise. In fact, I've reversed time because whenever I see minus nu, Laplacian u, I put plus du over dt. So I always write that. But then since it goes both ways, I got stuck. But I chose in the beginning that. But that's the wrong sense of time because the evolution of the dynamics, that's Fokker-Planck equation, it should be here with a minus, it should go forward. Here it's going backward. While the U equation, what is the U equation? The U equation is, if you know the whole history of the population, the U is the Bellman equation. That's what gives you your optimal decision. And in fact, that's exactly what choosing is about. When we choose, we anticipate. We anticipate with a certain horizon, which could be very small because it can be a myopic decision. So this is why either in those systems, I didn't write it, there is in the big MFG, MS-star equations, there is an additional factor, which is what is often called in economics a discount rate, or I prefer to call it the intertemporal preference rate, which is just to say, suppose I have a decision to make today, and what is the impact? How do I measure the impact of the decision in 10 years from now, in 8 years from now, in 5 years from now? So usually I take more into account what's going on next and less in the far future. When you're dealing with questions related to sustainable development, the rates are different. In fact, if you look at very important publications on sustainable development like Lord Stern report or the work by Roger Guenry, they are talking about ecological rates, they are talking about those things, and it's exactly what is the type of rate one should be interested. Here the rate is 0, which means that the future is as important as today. But if the rate is very large, this means the future doesn't count at all, that your decisions is almost instantaneous, and when lambda goes to infinity, you take your decision immediately based upon what you have as information today, and that's agent-based model, okay? So just to see how this is organized. It's a forward-backward system. It contains, as part of your case, lots of equations. Forget it. Okay, this I already described. Overview and perspectives, and then I'll switch off the computer, and then I'll tell you about machine learning. But before that, 2 silly examples. So there are lots of questions. Partial results exist, many open problems. Existence and regularity is a major issue. I already mentioned a little bit on this, a little bit what is known. Basically, nice things happen when there is some monotonicity assumption. Otherwise, you have lots of difficulties. So the uniqueness regime, say either small horizon, because that's just saying that even for an hyperbolic equation locally in time, it's well posed. And, but you can have non-uniqueness, non-existence, non-regularity. And that's where it gets tricky. I already mentioned that yesterday. But in fact, when you start working with people in economics, they are not like physicists. When you tell your physicist, listen, your model is very interesting, but it's, there doesn't exist a solution. He said, okay, okay, let me change the model. With the economics, you say, wow, super. What are all the solutions? And you look at him, you smile, and you say, okay, maybe in a couple of centuries, come back. So lots of qualitative properties, stationary states and stability, comparison cycles. There are very interesting issues around dynamical systems when the state space is finite. There is a justification of n going to infinity. Numerical methods, currently 3 general methods, and lots of particular cases. Okay, many possible extensions. Applications, we had so many applications that we made with Jean-Michel. 4 years ago, 3 years ago, we had a startup company. And it started with 1 employee. After all, mathematicians creating with a company, let's be careful. 3 years later, we had 30 employees, and we sold it because we could not manage it anymore. So that's, and we sold it to Havas. Havas is an advertising company, right? You might ask, what? A group of mathematicians and computer scientists working for an advertising company? Yeah, everything is becoming digital. You have advertisements everywhere on the web. You have high-frequency auctions for those advertisements on the web. You'd better have some models if you want to do things without losing your shirt. And then you want to more and more tune your advertisement to your customers, right? It's the right people with the right customers. Google does that in the usual Google way, doesn't tell you that it's keeping all your data and just throw you essentially what you've done the day before in a rather silly way. They are using machine learning, but it's not working so well because usually you make a reservation for an hotel with Google, and then for 2 weeks you get advertisement for the same location where you have already done your it's completely silly. That's a good example of the misuse of big data. But anyway, indeed, most of the applications were related to what is usually called, that's a fashionable word, big data. I hate this expression. I call them meaningful data. In the sense that it's not the fact that they are big, even if they are small, even better. But it's really, do they contain some information or not, right? So, and also we want to specialize in data which are being created by people. Because people do have strategies, okay? I think that's it. Those 2 examples and a little bit of some kind of view from Mars of machine learning. Okay. So at which time will the meeting start? Just to explain, then I explain a little more detail the OLA. So suppose that we have big number of people coming to a meeting. I already mentioned that. Mathematical idealization is going to be infinite. Okay. Random times to arrive. You know that if the meeting is not going to start on time, we are, as I said, in a civilized country, and you know that if you get there after the official beginning time of the meeting, you look slightly bad because some people might have been there at the right time. Okay, so you pay something, there is a slope. The later you come, more you look bad. But certainly you look much worse if you get there after the meeting has started. And the meeting will start when as I said, 85% of the people have come, just to give an example. So it's possible now you have all the data you need to put in our toolkit, and you can get some answers. Why did we care about this stupid example? It's in fact the reverse, and I want you to think about it, of questions which are related to the price of oil. So let's think about it. It's like dinner time. Huh? We are discussing it's very much related to the Hubert peak and the Otterling's rent, but I don't want to go there. There are discussions here whether there is a peak of prices and so on, but that's not something I want to say. But here is what I want to say. Certainly you have producers. It's more a stackable game. There is one big producer, lots of small producers, but let's forget that. Huge number of producers. And you ask yourself, what is the price of oil when 90% of the oil reserves in the world are gone? I mean, naively, people would say zero, infinity. And the answer is zero. I'm being slightly provocative. Because when 90% of the oil reserves are gone, you'd better have switched to other energy mechanism, right? You're not going to switch when you get the last drop of oil, okay? So think about it, and of course now you see the connection with meeting. The OLA, it's much more fun. Also, okay, I'm a former rugby player, so I'm discussing only rugby, Jaco, and don't worry. Huh? So here's how we approach the question. So the stadium is a circle. We are going to look So they are columns, and we want to understand what's going on through the columns. So the columns are being labeled. It's a parameter. That's not where the real action is taking place. X on the circle. Then here I'm going to put it's parameterized by X, but I want to have a density of people, a density of positions of people. So Z equals 0 means sitting. Z equal 1 means standing. And then Z can be between 0 and 1, and you're like that. I know, it's ridiculous. I'm going to make it maybe one more time, but no more. Don't ask for more, okay? So you have this density. So typically the order of magnitude is you have about 100 rows in a column, right, in a typical stadium, maybe more. I don't know about Maracana. I never went to Maracana. I mean, do you know how many rows there are? You don't know. Okay, so that's the first step of the model is what are the variables that we use in order to describe the agents. And then the criterion. Well, there is a cost for moving. Typical kinetic energy. Okay, natural enough. Then there is the comfort of the position. So sitting or standing is quite comfortable. In between, you won't stay like that for hours, right? So a steep negative quadratic if you want. And then you want herd behavior, mimicry. You want to be in a position which is the same as a position of the neighbors, okay? Which means that you add a term like half of z minus some kind of average. What is this average? So you're going to take a certain scale, x minus h, x plus h, which is more or less the number of rows you can see on your across you, around you, and that's normalized. And you look at xi m of y of xi d xi dy. Okay, and that's just saying that I want to be in a position which is like my neighbors. Okay, so everything has been prescribed. You can write down the equations. I won't write them down. You can analyze those equations, and here is a prediction, is that if you put a parameter which is herd behavior and you freeze the comfort and you freeze the length of the stadium, then if h is bigger, is not too small, there exists a unique, stable, periodic wave. Okay? In fact, it's unique up to symmetry going in the reverse side. Okay? So which means that if stadiums have basically essentially the same size, all over the world, the olas should always have the same speed. And the olas have been measured. I said there is a big literature on olas. In fact, there is a big literature on any question. But anyway, so there is a big literature on ola. And so the speed has been measured and experiments have been made. The speed has been measured, and you can find lots of articles on Wikipedia that give you the speed with 5 decimals. Okay? I'm a little bit suspicious about the decimals, but it indicates that they are somehow that it's somewhat fixed. Okay, so let's go back to the experiment. There is one I like because it also shows the difference between thinking that the agents are like particles and thinking that they are people. The experiment was made by Dutch statistical physicists. Why people are interested in OLA? Because that's the emergence of a coherent behavior in a big crowd of actors. So, and that's all those theories about emergence are very fashionable today. And so the physicists have these natural ideas. We love solitons. Okay, a wave looks like a soliton. So what is the main property of a soliton? Take 2 solitons, they interact, and then they will separate and continue going along their paths, right? So they had this experiment of creating in a stadium in Holland two waves, 2 olas, that went against each other, and then it was a major collapse. Of course, this is not a particle of fluids, those are people, right? So Picture yourself. You're sitting in the middle. You have two waves coming. What am I going to do? So clearly, that's because we anticipate and we are people, right? So I'm not saying that this model is correct. I'm just saying now we can discuss. It's not creating some kind of force between people and which is completely ad hoc. I'm first assumptions rational. Here are my variables, and here are the criteria. Maybe you don't like those criteria. Maybe you don't accept that people are rational, but at least you know what you're discussing about. Okay, so let me conclude. It's getting late, but I'm essentially on time. And I want to conclude with a few things taken from machine learning. And part of the always insisting upon the fact that we are dealing with humans. So you may be aware that a few weeks ago, New York City released all the information about cabs for a few years, indicating, giving all the data about pickup time, arrival time, place of pickup, arrival location, and the identification of the cab, not the driver of the cab. And in fact, there is, as I just said a minute ago, a big literature on taxi cabs. Because those are clearly agents that do a lot of strategy. Right? Where to wait for customers, where to go if there is traffic. Why do they get nervous after a little while? They know precisely at the time after which they are losing money, and so on. So there's been lots of studies in the United States about taxi cabs. Of course, involved in that, you have the issue of tarification, tariffs, right? And so it's not neutral. So that's why New York City is releasing the data. And the point is that if you forget that those are people that do some strategy, you may get the wrong type of tariff, because whenever you propose a tariff, people will try to optimize in view of the new tarification. So it's not going to be exactly the same behavior. If you don't take this into account, you're going to miss the picture completely. You don't believe me? Let me give you an example. A very simple example. You want to see what are the typical waiting time, the lines for cab drivers, especially in particular locations. For instance, Roissy Airport in Paris, right? You have, very often they have to wait 2 hours before picking a new customer. You take this data for granted, you miss the picture completely, because after a certain time, all cab drivers will say, I won't stay at the airport, I'll go back to Paris, right? So if you just look at the number, you're not seeing the right picture. Another example, it's the numbers of unemployment in many countries, including United States, because you can register if you are unemployed in the States, don't get any money, but possibly some job offers. When the economy bounces back, so jobs are being created, the official number of unemployed people grows, because then people go and register, because they might have more opportunities. So the point I want to make is that it's very important to remember that, in fact, people trying to optimize, to do some strategy. Anna, is that late? It's already tomorrow morning. Okay, so, but anyway, to cut the story short, let me say that we have been dealing with trying to have mathematical models that indeed implement the fact that people have strategies. But before even going into that, I want to tell you a few stories about classical methods or classical problem in machine learning. One is K-mean, the other is EM, expectation minimizations, and I want just to explain in rough words why those are natural game theoretical situations. In fact, if you look at the machine learning literature, a lot of the vocabulary of game theory is being used. What I claim is that models are also natural. K-mean, let me explain this very briefly. So you have a bunch of points, large number of points, xi, from 1 to n. And you want to find k barycenters. So let me denote those guys by xi, k barycenters. EM is about having a density which is a superposition of several probabilistic densities, and you want to recover the coefficients out of the observations. A k barycenter, what does that mean? So that's y1, yk, and what you want to do is you want to split this set of points in classes, clubs, if those were people, and so the xi is going to be in class cy, so it's a partition of the set of points. If xi minus let me call this yj, xi minus yj is strictly less, well, we have to worry a little bit about equality case degeneracy, but let's not worry about that, minus x y alpha for all alpha different from j. So being in a class is being measured by that you're closer to one point than to all the others. And second fact is that yj should be the barycenters of the xi in the cj class. Okay? So how to cluster the information in some sense. So it's a basic problem in machine learning. I'm not saying it's useful. I'm just saying it's a nice way to think about clustering. Think about it. What do you have? People are competing. The Y guys are competing with each other to attract as many people. Right? Now, this is about data. There are no people. Right? But still, you can think exactly as with the eigenvectors, that you have vectors which are competing, or the eigenvalues that are competing to minimize the equadratic form. It's just using a game theoretical framework in order to produce a model. So if I take k-mean EM, in the end, I can even have a distribution, a continuous distribution in terms of initial information. And here's a typical steady state problem one find, which is something like rho is some relaxation parameter that I don't want to describe. I'm sorry, alpha rho I plus a divergence of rho I ui. Possibly you have a minus nu Laplacian u. Let me put a minus nu Laplacian u equal here some kind of df over du lil f. That's the data. And alpha ui minus Laplacian, that's rho I, sorry, minus Laplacian rho I, so it's df over dui, plus, and that's ui, sorry, plus gradient ui square, and equal, and here you have a certain function that may depend on I, and that depends on rho I. Okay? So typically here in the barycenters problem, what you have is here a function which is just a distance to the center of mass of the rho I. That's it. And you have your model. What is the f? Well, the f is a criterion with which you're going to decide in which class you want to be. So that's a criterion. All the rest is essentially the two elements that make the model out there. And the f, typically as an example, you should think it's the one that is going to give you the maximal reward. Okay, maximizations of uj. For EM, it's a more complicated expectation, which is related to probability theory. I don't have time to mention that. So what is the point? The point is not so much that to have a crazy, by PDEs and Minfield games, interpretation of those classical methods for which very efficient algorithms exist in the literature. That's not the point. The point is to try to make a model which will then help us to design better algorithms in the sense that they will be more relevant for the applications because of the reasons I mentioned, especially when one is dealing with people that indeed try to anticipate, make some kind of optimization. In fact, just to conclude, there is nothing Euclidean. Here I wrote in Euclidean space very often for social networks, you don't have natural distances. In fact, you want to create distances. And this is tricky. One of the applications we had was for Warner Bros. And with a special club, a Facebook club for Warner Bros. And the point is that clearly when you want to see that people are close, this is also related to how close are movies, when they want to say they like movies or they don't like movies or whatever. So clearly if you take one person that likes Harry Potter 1, another person that liked Harry Potter 2, you may say that in some sense they are close, okay? And that's a little bit tricky. You have no natural distances when you're dealing with people, when you're dealing with items and so on. So somehow they have to be created, those distances, along the way of the model, as you build up the club and you build up the distance. So it's a complete fixed point min-field game-like. But the first thing is that on a graph, what do you do when you have those typical forms? You have more general models than having these, but let me just show you the type of question. Now, for each of those UI guys, we have a bunch of sites which are on the graph. So we have now functions, values at those sites. What is the correspondence of that? Well, here's a simple trick just to conclude that circle of transformation. If you do e to the u minus Laplacian e to the minus u, you, of course, get minus Laplacian plus gradient u squared. So now Laplacian, you know what it is on the graph, and so you know what is the natural model on the graph. What it is simply saying that minus Laplacian is a sum. You have to decide on what are the neighbors, possibly the whole population you're going to look at. And there you look at ui minus uj. Normalized sum if you want. So that would be a typical, the typical analog of a Laplacian, right? And so if you play that game, what are you going to get? Well, you're going to get something which is a sum of a certain class of j's of e to the ui minus uj minus 1. And that's quite a typical form replacing these PDE terms. And if you want to solve this numerically, what do you do? Well, you add time. That's why alpha is also a relaxation parameter. You add time, and so you are just solving a bunch of ODEs. It's very simple, completely parallel. And that's not so hard to do. So then it's not at all about numerics. It's really about modeling. Well, how are we going to say that people are in the same group or not the same group? In a Euclidean space, you have natural notions of neighbors. In a more complicated setting, this has to be created along the way with the min-field games. That's a very long story. I just wanted to give you a little bit of the flavor of what we are trying to do. It's certainly we are not pretentious. We do not pretend that on classical problems in machine learning we're going to do better than what computer scientists have done for decades. But we can attack problems that they don't know how to attack because we can make models. And also we can incorporate what I like to call the human factor in those models and this possibility of anticipation. So I wanted to conclude with very concrete things. If your taste is more about mathematical theory, believe me, there are thousands of open problems. And if your taste is more into numerics, also, given an arbitrary MFG, I cannot guarantee that we'll have a numerical method working for that problem. We have 3 general methods that cover some ground. So there are, as I said, a huge class of models, but lots and lots of open questions. And that's why it's an endless project with Jean-Michel Lasry. Fortunately, and now many people are getting in this game, and fortunately, there's probably, I would say, 3, or of course there are meetings all the time, but they probably 3 to 4 meetings a year on min-field games nowadays. So I'm afraid we have created an industry. But anyway, time for the cocktail. Finally, some good news. Thank you very much for your patience.
very much, Pierre-Louis, very provocative, more than ever. And,
My age, I can afford to be provocative.
right. So we are opening the floor for a few questions.
Even if
Please,
you don't ask questions, you are also right to go to the cocktail.
that's right.
It's the same joke as yesterday.
Questions, comments? Very objective, please.
Is 12 meters per second.
I'm sorry?
The Mexican wave is 12 meters by second. This is the average, okay?
Oh, you checked it. I saw you opening
Yeah,
your...
yeah. But it
your-
goes clockwise usually. Do you have an explanation why?
Wait. That's very interesting. I have to confess that I asked one of my friends for South America. I don't remember if he was a Brazilian or Argentinian. It might have been Argentinian, sorry. But anyway, yeah, I asked him, what about the ola in your when you go to a game in Argentina? Does it go in the same way? You know, then you start thinking about the water in the sink and so on. And in fact, there were two Argentinian guys, and they started screaming at each other, saying, "No, it goes this way, the other way." Not clear. No, but it usually goes always the same way. But I tend to believe it's because the majority of people are right-handed. So that's my personal explanation. I thought about it, but an experiment was made during the Olympic Games in Sydney of a counterclockwise ola. It went on perfectly with exactly the same speed. Okay. So the uniqueness up to a change of rotation is, well, anyway, don't believe my, remember, I told you about Orson Welles in the beginning.
Question?
What
Comments?
I said might even be true, right?
Suppose you have you start from this system of players, and the initial configuration M is not the Nash equilibrium. Is there a natural dynamics which?
Okay, that's very complicated. In fact, you may raise the questions. Let's keep the ola. You know, I cannot write a model which will tell you how the ola will start from out of nowhere. It's a stable periodic wave. It has a certain domain of attraction, but this initial build-up, I don't know. Okay, and also breaking up. In fact, this is just a mean field theory. So you know, if you discuss with physicists and you mention mean field theories, at least in physics, they laugh. I mean, this is just the beginning. The action is no more there. The action is in phase transitions, or think also large deviations in more probabilistic setting and so on. So this maybe in another life, this is absolutely fascinating. And typically the ola breaking might be much more related to a phase transition. It's also the case that suddenly in some of those phenomena, a small group of people become important. So here I'm in a situation where all the players are neglectable. So I don't know. The bottom line is I don't know.
I have a question for you concerning this interaction to industry. You mentioned that MFG started as one person,
Sponsored,
then
no, for the startup, yeah.
Yeah, and then ended up being sold to Avast, I suppose. How was this interaction? I mean, from the mathematical point of view, you gave a very good talk, but how about this interaction in the industry?
I'm like an iceberg. The mathematical part you see,
Yeah.
just one part of my activity. So I've always worked with industry in all possible ways. Okay, contract with my lab, consultant, chairing or being a member of scientific advisory boards, members of board of directors. I've done everything with industry. So first of all, there are no rules. Okay, so you have to adapt. Your neighbor knows also very well how to interact with banks, with financial institutions. There are lots of modes. There are no general rules. It depends on the type of projects and so on. Here, in the context of a startup company, it's very hard because forget the maths. I mean, they don't care. I mean, the maths may open a few doors because, okay, especially in a small country, they may be aware of that there are good mathematicians and so on. But in the end, you have to produce something. And around big data, it's a little bit complicated because most companies know that that they should look into big data. They don't quite know what to do, how to do. So there are lots of discussions. So it was endless discussions. In the end, we were lucky because we got, for reasons which are too complicated to. Well, the first thing we did is what we had a good connection with Facebook. So we were one of the, they called the privileged developers of Facebook, and one of the 3 in France. In fact, when Zuckerberg 2 years ago made these annual presentations for investors, MFG was sitting just behind the logo, was just behind it. So that helped. Okay. Still not enough. So because of Facebook's Warner Bros. Came to us and told us of their grand plan. And so we did everything, the whole chain, including the site. So we had young guys doing the design of websites, like architects and so on. People doing all the computer science tubes, collecting data, preparing data, because data is very often a mess, so you have to clean data. Then all the system which is related to keeping the data, using it, we are using the Amazon cloud.
So it
and then mathematicians that do the algorithms. So it's a whole chain. It's not only about mathematics. So in the end, we did the whole chain, and then they told us, okay, now we are going to test it. Here are 10 cases or things that we are selling. Warner Bros. Is selling, like DVDs and stuff like that. Can you use your data to improve the sales? Okay. So we had 10 cases. We had 1 engineer working on each case for 1 day. In a week, we went back to them, and they made observations. And the sales were multiplied by a factor ranging from 2 to 10 for all 10 cases. And then we sold the company.
So you had a product somehow.
Because we had made the proof of concept. And then it was another adventure which is not our interest. So because everybody is discussing about those things, but let's do it, and let's do something which works. And we got lucky. Honestly, I think we got lucky with Warner Bros. We got very lucky with Facebook. But one funny thing is that we created Buzz because we have a software. You can even download it if you want, which is, because we work a lot on Twitter also, which is where does my tweet go? To visualize how it's going to spread, what are going to be the influential people that are spreading the tweet. And we made a little bit of noise because we analyzed everything that took place before the media. I got into it about a famous former French minister of economy, which was involved in a weird incident with the room service in an hotel in New York, and her name is DSK, the pig. In fact, the whole operation started on the information broke out on Twitter. The media, the radios, that was 6 or 7 hours later. And then we were able, by tracing, you can absorb all the data of Twitter, everything. It's a few terabytes a day. It's nothing. You absorb everything, no confidentiality, forget it. So you get everything, it's accessible. And so we could analyze who were the crucial people from which the information are spread. And in fact, we even identified a person, which is a deputy from a right party that was in New York.
So that will be used for elections, for example.
For?
Elections.
Of course. Listen, Obama won the, it's not a propaganda, it's fact. Won the second elections because he has teams of data scientists working specifically on a few states, which were the crucial ones. And he won because of that. Not only because of that, probably, but certainly played a very big role. We acknowledge that. Well, I could go on with those stories, but let's have a drink. No?
So let's start.
It was fun, huh? En plus, au passage, il y a des